So hello, everybody. Welcome to today's IRENA online seminar. I'm Linda Lombardo. I'm a postdoc at the University of Trieste, at INAF, University of Trieste. And today I will be the host of this seminar. Today's speaker is Marta Molero. She's expert in chemical evolution models. And Marta is a postdoc at the TU Darmstadt, and she's working in the group of Arcones. Marta did her studies in Trieste, both her master and PhD, under the supervision of Francesca Matteucci. So thank you, Marta. I think you can start, and we'll be happy to hear about your work.
Thank you, Linda. Thank you, everybody, for the invitation. I'm Marta Molero. I'm a postdoc researcher at TU Darmstadt in the group of Arcones. And I mainly work on chemical evolution models, in particular of neutron capture elements. So during the talk, this talk, I would like to give a bit of introduction and overview of the latest research on this field, and then something new that with my group we are working on. So the field of chemical evolution is a field in astrophysics that studies the evolution of the abundances of the different chemical species in the interstellar medium of different environment, of galaxies of different morphological type. This evolution, of course, is influenced by the galaxy evolution itself, but it's mostly influenced also by the stellar evolution and the stellar nucleosynthesis. So stars form out of molecular cloud of a certain chemical composition, and we can say that we broadly form two categories of stars: massive stars and low intermediate mass stars, depending on their initial mass. Low intermediate mass stars can be single stars or can be found in binary systems. In the case of single stars, during their asymptotic giant branch phase, they will produce some light elements and some S-process material, in particular main S-process and strong S-process, so elements like cerium, lanthanum, barium, and all the way through lead. On the other hand, when you find them in a binary system, the low intermediate mass stars, they can give rise to a type 1a supernova event, which is mainly producer of iron and iron peak elements, or they can give rise to a nova event, which is mainly responsible for the creation of lithium and some radioactive isotopes. On the other hand, when you have massive stars from 8, 9, 10 solar masses on, they can die as classical core collapse supernova, producing alpha element and iron, or they can be as subclasses of normal core collapse supernova. During this talk, I will often refer to magneto-driven, but this doesn't exclude any other possible rare subclasses of core collapse supernova. And magneto-driven might be a powerful source of our process material. Both from a magneto-driven and a core collapse supernova, we can have a neutron star as a remnant, and then if we have a neutron star binary system, likely in less than a Hubble time, this will have a merger, and from this merger we can have a production of our process material. So stars of different mass, they die at different time and produce different chemical species. They enrich the interstellar medium with these newly fresh products of their nucleosynthesis. And from this new molecular cloud, now with an enriched chemical composition, a new generation of stars will born. And the process will be repeated. And this is the concept at the base of the chemical evolution. So if you want to follow the evolution of the mass of gas in the interstellar medium of a galaxy in the form of a chemical element I, then you have to solve a differential equation, taking into account how this amount of gas is added and subtracted from the interstellar medium. So this is a quantity that it's depending on time, of course, and also on space. As for example, in this case, it's depending on the galactocentric distance and on the angle theta, but if you also want a dependency on the altitude, then you refer to 3D models of chemical evolution. So you start by accreting gas from the intergalactic medium towards the interstellar medium through infall phenomena. Then, depending on the gas you lose, on the galaxy, you lose gas from the interstellar medium towards the intergalactic medium in the form of galactic winds. And then depending on the system, you might have some loss of gas by feeding the central supermassive black hole. And then, of course, you lose gas from the interstellar medium to form stars, so because of star formation processes. And as we said, different stars at the end of their life, or even during their life, through stellar winds, they will give back gas into the interstellar medium, enriched gas. So now if you want to solve this kind of differential equation, you need a chemical evolution model. There are different chemical evolution models in literature, homogeneous models, they can be one zone or multi-zone system, but each system is an homogeneous zone. Then you can have stochastic or inhomogeneous chemical evolution model. They are multiple zone chemical evolution model. Each zone is homogeneous, but they evolve independently one from each other with a stochastic sampling of the stellar mass distribution. And then if you have enough time and enough computational resources, you can integrate the chemical evolution equation with dynamical process in a self-consistent cosmological framework, and then you have chemodynamical simulations. In this talk, I will refer to homogeneous chemical evolution models. So when you observe an abundance of the element on the surface of a star, of a main sequence star, that is representative of the composition of the interstellar medium when the star is formed. And because of that, stars can be considered being fossil records of past events, and we often refer to the field of chemical evolution as galactic archaeology. So if you observe a population of stars instead of only one star, then you can actually track as a function of time the evolution of the abundances of the element that you are observing in these stars. And for example, you can plot them in a parameter space like the following. So here we are observing the abundance of the europium and the abundance of the iron, and we are creating this abundance, this parameter space, which we read as the europium over iron versus iron over H. This is, of course, square brackets notation, so we compute the abundance of an element, divide with the abundance of the other one, and we compare that to that observed in the sun, so that the sun is in 0, 0 in this parameter space. So if we look at the europium, this is because we are interested in tracking the R process nucleosynthesis. And why we choose europium? We choose europium because europium is the only almost completely R process element which has enough stellar observation. So to actually have a statistically meaningful comparison with the chemical evolution model. And when we plot what we observe, what we usually see is this plateau towards intermediate to low metallicity, followed by a decrease. So we can refer to the axis of the iron over H, which I will often call metallicity, but we can use that to take track of the time. So metallicity grows as time passes by because of the stellar generation coming one after the other and enriching the interstellar medium. The relation is not strictly linear, but we can say that towards here we are at early times, and then we have solar metallicity, and then present time. So the fact that we observe a plateau from intermediate to low metallicity, this means that the europium and the iron are produced on similar time scale, not necessarily by the same event, but by similar time scales. And then from iron over H minus 1 in the Milky Way, more or less we have this decrease, which means that the iron is produced more than the europium. So if we want to model and try to reproduce this pattern that we see, this trend that we see, then as a first thing, let's understand where the iron comes from. So iron is produced from a quick source, which is classical core collapse supernovae. They are quick because they come from massive stars, so they have short lifetime compared to the evolution of a galaxy, and they explode soon in the galactic history, and they are mainly responsible for polluting iron at lower metallicity, intermediate metallicity. And then again, from iron over H minus 1 in the Milky Way, we have the arrival of type 1a supernova. They come from low mass stars in binary system, So they are delayed scenarios, delayed event. They are the main producers of iron in the galaxy, and they will maybe be responsible for this decrease that we see here. Okay, now we have to understand where the europium comes from. So if we want to start from an observational point of view, then the only observation that we have is that of the neutron-star merging event of 2017. So following this event, there has been a kilonova event. And Watson et al. In 2019, in the reanalysis of this kilonova, they were able to measure the amount of strontium which is produced in this event. So strontium is technically classified as an S-process element, but all neutron capture elements are made by both the S-process and the R-process, and being this a neutron-star merger event, this is the R-process component of strontium that we are observing, and it is around 10 at minus 5 solar masses. So if you scale this R-process component of strontium with the R-process solar distribution, then you can obtain the europium. So you can say that in this event you produce 10 and minus 6 solar masses of europium. So now we know how much europium is made, by which site. We have to understand when this site actually appears in the chemical history of our galaxy. So the delay time for neutron-star merger is given by two components: the lifetime of the secondary component of the progenitor binary system and the gravitational radiation delay. So concerning this component, we start with a binary system made of two stars, massive enough to go through their life, die as a core collapse supernova, and leave a neutron star as a remnant. So first the primary star will go through its evolution, so the most massive, and then the secondary star. So the secondary star gives the clock of the system, and when this explodes, it's the time at which we actually have the formation of the neutron star binary system. And this is an easy term to compute because there's a strict relation between the mass of the star and the lifetime of the star. On the other hand, for what it concerns the gravitational radiation delay, so namely the delay due to gravitational wave radiation, this depends on the mass of the primary component, the mass of the secondary component, the initial separation between the two stars, and if we are not in spherical symmetry, also from the eccentricity of the system. So it is easy to understand that if I have a galaxy with a different neutron-star binary system, each of them having slightly different properties, then each of them will have a different gravitational radiation delay and therefore a different delay time. So that in order to take this into account, I need a delay time distribution function. Okay, so now we know that neutron-star merger make europium, we know how much europium they are making, and we know when they appear. But how many merging events I have in the galaxy, for example. Then to know that, I have to compute the rate of neutron-star merger, which is actually a simple calculation, because this is just once I understand the shape of my delay time distribution, then I can just compute a convolution between a given star formation law and a given delay time distribution. This is a normalization constant, and this is a term which depends only on the initial mass function. So if I know the galactic properties of my environment, of my galaxies, namely if I know the initial mass function and if I know the star formation, then I just compute the convolution between the delay time distribution, the star formation, and I have the rate of neutron-star merger. And the powerful thing about this simple way to compute this rate is that if I change galaxy, I'm no longer in the Milky Way, and it happens that I know the star formation, the initial mass function for this galaxy, then I can predict the rate of neutron-star merger in a new galaxy. Okay, so now we know everything, we plug everything in our chemical evolution model, and this is the results. So here I'm showing you with this line results of the chemical evolution model in the case in which europium is made only by neutron-star merger. So you can see that there are different negative aspects here. So first of all, we are missing the plateau, especially at very low metallicity. And here in general, we are producing an increase rather than a plateau and then a decrease. And most important also for the lowest curve in particular, which represents results of the model in which I have more system merging with longer delays. Here at high metallicity, I produce a rise instead than a decrease, because the late contribution of neutron star merger of europium actually completely counterbalance the production of iron from type 1a supernova. So it's either that all neutron star binary systems merge on extremely low time scales, or they cannot be the major producers of europium. And this is a well-known result, both in chemical evolution and in nucleosynthesis, that actually dates back to more than 20 years ago. So we need a quick source. This source can be a subclass of core collapse supernova. So massive stars, magneto-driven collapsers, it's important that it's quick. So here, for example, I'm showing you the europium over iron versus iron over H, observed with the data from the sculptor dwarf spheroidal galaxies. In this paper of 2021, we were studying several ultra-faint and dwarf spheroidal galaxies. You can see that even in sculptor, we can observe kind of a plateau followed by a decrease. So data are less, but a similar trend to that observed in the Milky Way. And the different lines are results of my chemical evolution model, in which I use only magnetorotational supernovae as producers of europium. So we have only the quick source, no delayed component, and different lines are for different nucleosynthetic calculation for the production of europium. And you can see that not only we can nicely fit the observed trend, but we don't need a delay time. We don't need a delayed source. In the sense that the quick source completely dominate the scenario. Indeed, whenever we add the delay source, so here we have both delay neutron star merger and quick magnetorotational supernova, we still get a nice agreement with the data. Then here in this paper, we also studied the peculiar observation of europium, barium, and strontium of the reticulum 2 ultra-faint dwarf galaxies, here shown in black. Here, reticulum, it's an ultra-faint, very small ultra-faint dwarf galaxies that shows overabundance of neutron-capture elements with respect to the other ultra-faint dwarf galaxies. Here, the colored data, and compatible with some of the most high stars observed in the halo. So halo stars are the gray dots here. And here, as suggested also by G et al. In 2016, we were able to fit these abundances by assuming a quick source, and in particular only one event of a very quick source, producing something around 10 and minus 6 solar masses of europium, even though the reticulum case can be more complicated than how we solve it in 2021. Okay, now we know how to model our process because we know how to model the europium, how we confirm that what we did is actually correct. Then we look at the other neutron capture elements. All the neutron capture elements are made again by both the S process and the R process. So we can take, for example, a survey which has enough observational data, as for example the Gaia ISO survey. Here we were taking the 6th data release that provided us with almost 4,000 field stars and around 60 open clusters, and in particular that gave us observation for different neutron capture elements. We had yttrium and zirconium on the lightest part, then molybdenum, barium, lanthanum, and cerium, praseodymium and neodymium, and then europium. So you can see here the europium over iron versus iron over H as observed in the field stars in gray and in the open clusters here colored. The open clusters are color-coded according to their position on the galactic disk. We have magenta open clusters belonging to the outer part of the galactic disk, green open clusters belonging to the solar neighborhood, and blue open clusters belonging to the inner part of the galactic disk. And even if data are fewer than what I was showing you before, here again we can see some sort of a plateau followed by the decrease. So again, we need two sources. We need a quick source, which can be in my case magneto-driven, with some yield prescription from the literature and some rate, usually a low fraction of normal core collapse supernovae are assuming to die as magneto-driven. And then we have our delayed source represented by neutron star merger. With that, we can have again this plateau followed by decrease. We can also divide our galaxies in different rings and compute the chemical evolution in the outer, local, and inner part of the disk as well, and also as a function of the age of the stellar population that we are forming. The S process, similar. We have a quick source for the S process of rotating massive stars, and then we have a delayed source for the S process, which are asymptotic giant branch stars. So let me spend a few words on rotating massive stars. Here I show you the yttrium over iron versus iron over H, and the barium over iron versus iron over H in the case in which I shut off the R process, so only with the S process here, from AGB and rotating massive stars. Rotating massive stars with three different initial rotational velocities, so 0, no rotational velocities, 150 kilometers per second and 300 kilometers per second. The effect of rotation is clear, is that of increasing the production of S-process material, especially at low metallicity and especially for elements belonging to the first S-process peak rather than the second S-process peak, for which we have to push the rotation to 300, to the high value of 300 in order to see a high increase. Now let me spend some words also on the number of progenitor stars that we have both for AGB stars and rotating massive stars. You see that for AGB stars we have more than 100 progenitor stars spanning different mass and metallicity, and a similar number for rotating massive stars spanning different mass, metallicity, and rotational velocities. And this is very important for chemical evolution model. Here, for example, I'm showing you a work from Finia Jost, a PhD student in our group in Darmstadt, where she computed core collapse supernova neutrino-driven wind yields that then we propagated into galactic chemical evolution models. She computed that for different metallicity. Here I'm showing you the predicted production of iron as a function of the progenitor mass. This is solar metallicity. She gave me different values of metallicities and different explosion energy. And you can see here, for example, for the progenitor mass, that she gave me progenitor masses with steps in the mass of even only one solar masses, as for example, going from 11 to 30 solar masses. And then all the way through 70. And this is very important for chemical evolution to have such a fine grid of progenitors, because in the chemical evolution model, whenever you don't have progenitors, the model interpolates, creating extra uncertainties on our results. So going back to the rotational scenario of massive stars, the correct way to include them in a chemical evolution model is similar as with neutron star merger. We had a delay, we had a distribution of delay times. Here we have a distribution of rotational velocities. Generally, distribution prefers higher rotational velocities towards lower metallicity. We implemented the first one that has been done by Pranzas et al. 2018, but all of the others that you can find in literature that came after resemble this one, and they all agree on the same general results, that we need to rotate faster towards lower metallicity, as for example in the case of the work of Donatella Romano in 2019, where she tested this against CNO isotopes, Federico Rizzuti in 2021 with S-process galactic chemical evolution model, and also myself last year, trying to fit the metallicity distribution function of the galactic bulge, and earlier this year in the context of chemical clocks. So again, here I show you elements belonging to the first S-process peak, strontium, yttrium, zirconium, elements belonging to the second S-process peak, barium, lanthanum, cerium, and in blue there's the S-only component, in the case in which I shut off the R process, and in green we have both of them. And again, you can see how the effect of massive stars is present here for the lightest elements, and is not here for the heavier one, in which the shape is mainly given by the strong dependency of metallicity from the yields of AGB, So in the end, you can take all of your observational data for your neutron capture elements, and you can divide them in the outer, local, and inner part of the disk, compute your chemical evolution model, and as you can see, in some cases we have nice agreement with the results. In some cases we face some underestimation, some imperfections, some discrepancies between our model results and the observational data. So in the second part of the talk, I would like to talk about the most recent research we are working on in collaboration with Almudena Arcones, Fernando Montes, and Camilla Hansen. So until now, we got how we can model the R process in galactic chemical evolution. So we want to fit the europium, of course, but we also want to have a nice fit with the other neutron capture elements. And to do that, we understood that we need both a quick source and a delayed source. Nevertheless, we have many uncertainties in almost all the parameters that are shaping these two different sources. For example, in the case of magneto-driven, we can surely rely on nucleosynthetic calculation for the yield of europium, but it's also true that many different calculation provides many different results. And on top of that, their rate is not observational constraint. And similar for neutron star merger, we have an estimation of their rate, which is actually based on only one event and therefore has a very big statistical uncertainties. And at the same time, if you remember at the beginning, I said that we have measurements of the strontium produced in the neutron star merger event that then we scale with the solar R to obtain the europium. So this makes me jump on the third point here, scaling the strontium, which is observed to get the europium. Basically, it's implicitly assuming that the universality of the R process, which is usually defined between the lanthanides and the third peak R process elements, can be extended all the way through the lightest elements as well. And on top of that, we don't only want to fit the europium, but we want to have a nice fit with all of the neutron capture elements, for at least for the one for which we have enough observational data at the same time. So this is the motivation for this work. For the first point, in this work, instead of assuming a fixed nucleosynthetic channel, we've been more agnostic. We have a parametric approach in which we build a large grid of chemical evolution models varying the main parameters which affect the R process injection in the interstellar medium. Because of the fact that we want to fit many trends at the same time, we will treat each trend. Each trend is a different objective that we want to follow, so that we want to reproduce, so we will treat the problem in a multi-objective context. For the last point, the solar scaling, we will keep this assumption for all of our models in order to test the validity in this assumption and to actually see if that allow us to still get a nice fit even of the lightest neutron capture elements. So now I show you how we write the R process contribution to the production of a given element I. So this is similar to the rate of neutron star merger that I showed you before. So now we can write that this contribution is given by two main terms, this one and this integral here. So this one is simply the yield of a certain element I made by the R process. So for example, the europium yield. And this is the rate of stars which will be allowed to produce this amount of our process of that element. This is the star formation, this is the IMF, and therefore this integral is giving me the number of stars in the mass range between ML and MU. And this number of stars will be, or a fraction of them, will be allowed to produce this quantity. I have an extra delay time here, tau, which is the delay between the death of the stars and the actual pollution with the europium. And this actually can allow me to, from this parametric scenario, actually have a correspondence to real physical events, in the sense that if, for example, this tau is set to 0, and we are, of course, in the massive star range with high enough europium yield, then I'm resembling a scenario which is consistent with a magneto-driven supernova. On the other hand, if I have very big delay times, And then this is in the range of masses that can die as a core collapse and leave a neutron star as a remnant. Then I'm resembling a scenario which is the neutron star merger event. So I take this important parameter, the europium yield, the R process europium yield, the stellar progenitor mass range, the delay time on top of the stellar lifetime. This is the stellar lifetime of the star. So an extra delay time, and an eventual fraction of stars, in the sense if I don't want all of the stars included in this range to actually produce their process, or only a fraction of them. Then I vary these parameters, I create a combination of these parameters for a total of around 10 at 5 runs of our chemical evolution models. So now we take all of our chemical evolution model, and first, before jumping into the multi-objective approach, we study the single objective approach, namely the europium again. So here again, I show you the europium over iron versus iron over H. We have some observational data in gray, and then we can divide the metallicity axis in different bins, and then we can compute the mean average of the observational data in each bin. Then I take all of my run, I compute a simple chi-square, and here I plot the best 100 model that I get. So I don't want to spend too much on actually discuss which is the value of the best model, but surely we can observe something that more or less we already knew, in the sense that quick sources are favored, so low delay time, short delay time, massive stars, of course, towards the lower mass end, so between 20 and 30 solar masses, with a production of europium of the order of 2 times 10 and minus 7 solar masses of europium per event. The fact that we actually prefer quick sources is not a surprise. We already discussed it in the context of dwarf galaxies, of local group galaxies, that whenever we added the magneto-driven scenario, alone or together with the neutron star merger, it was dominating the europium production. And as a consequence, if I just have a parametric approach, the models that will be favored will be the quick ones. So now we have our best models. And then what we do is we take the europium yield that we got for our best models, we scale that with solar R, and we get the yield for other neutron capture elements. Some light elements, strontium, yttrium, and zirconium, and some light but not so light elements like barium, lanthanum, and cerium. So we are moving from europium towards the lightest part. So again, the blue line is in the case in which I have only the S process and shut off the R process, and the green line is in the case in which I have both the R and the S process. So what we can see, let's first talk about the positive aspects, is the sun is reproduced. So here the sun is in the orange, in the origin of the parameter space, and our green line is passing through the origin. On the other hand, except that for yttrium, the more we move towards the lowest metallicity side, the more we underproduce the observed trend, with the most critical case represented by zirconium. In generally, zirconium and strontium have a worse agreement with respect to barium, lanthanum, and cerium. Again, zirconium is the most dramatic case. So since zirconium is the most dramatic case, let's see if there is some room in the choice that we made about our parameter to actually have a nice agreement between europium and zirconium at the same time, or at least a nice compromise before confirming that the solar scaling cannot be extended all the way through lightest element. Okay, so here we go step by step. There is a lot of information in this slide. So here we have, again, the europium over iron versus iron over H, and the zirconium over iron versus iron over H. We take all of our model, and we compute the chi-square for the europium and the chi-square for the zirconium. And we plot here them one against the other. So we have the chi-square of the zirconium against the chi-square of the europium for all of our model. And we can see that in the lower left part of the chi-square parameter space. Here I colored in magenta some models. These are the so-called Pareto front models, and this is a line which we will refer to the Pareto front surface, which is defined by the fact that it contains all of the model for which improving one objective will cause a worsening in the second one. What does that mean? That if, for example, I take one of these model and I want to improve europium, this means moving towards the lower values in the x-axis, but moving towards the lower values in the x-axis automatically corresponds to moving towards highest values in the y-axis. So improving europium causes worsening zirconium, and the other way around. So let's go back to these trends. So here in green, I show you the best europium model that I was showing you before. And here it's its correspondence with zirconium. And we see what I showed you before, that the best europium model is giving us a severe underestimation of the zirconium trend. We are doing the same thing for the blue dashed line here. This is the best zirconium model with the chi-square of 2 and its correspondence with the europium with a very high chi-square. Of course, the best zirconium models is giving us an overproduction of the europium. In magenta, there are all the Pareto front models. So the Pareto front, what is actually doing, they are trying to enhance the production of the europium, to raise these curves up in order to enhance the production of zirconium and have a nice fit with zirconium over iron versus iron over each. Nevertheless, what happened is that the Pareto front model that can reach this nice fit are at the same time the one which give us a very bad fit with the europium, a severe overestimation. We can judge the quality of the best Pareto front model. From the Pareto front model, which is the best, is defined as the one which has the closest distance to the ideal point, which is the origin in this chi-square parameter space, which here is in the darkest magenta. You can see that it's true that we got an improvement in the agreement with zirconium, for which I am not satisfied at all, just by eye, and this cost us a severe worsening of the agreement with europium. So now we can repeat the same exercise in 3D. So now we take three different elements, even independently from europium. So now we have barium, lanthanum, and cerium. And here I compute all the Pareto front model that, of course, in 3D will be a surface instead of a line. And in the different plot here, you can see that in black, there is the best barium model, the best lanthanum model, and the best cerium model. And in magenta, there are the Pareto front model. In this case, on the other hand, we have a nice agreement between the two models. They are very much similar, and it's easy for the Pareto front to find few models for which we have a very nice agreement of all the three elements at the same time, meaning that there is coherence between these three elements, which is not technically a surprise since they belong to the same peak. But nevertheless, whenever we look at the lightest elements, so strontium, yttrium, and zirconium, we don't have the same nice agreement. You see that the Pareto front model, again in magenta, they can overestimate the yttrium, in particular towards lower intermediate metallicity, still don't have a nice agreement with the zirconium, and they have more or less a decent agreement with strontium. So the same coherence that we observe for barium, lanthanum, and cerium is not observed for the lightest elements, strontium, yttrium, and zirconium. So now we move to the complete case, so 4D, for which of course we cannot show any plot of the chi-square parameter space, but we now have the Pareto front models for europium, zirconium, yttrium, and strontium, for europium, cerium, lanthanum, and barium. We observe similar conclusion in the sense that here for the lightest element, in order to have a decent agreement with strontium, yttrium, and zirconium trend, we had to increase the europium production to move towards higher value the zirconium and the strontium, which were underestimated, but this cost us the agreement with yttrium, and we lost the agreement with europium to get a not so satisfying agreement with the zirconium. On the other hand, when we repeat the same exercise for heavier neutron capture elements, barium, lanthanum, and cerium, we get that we will lose a bit of the agreement with europium, but the loss is not as dramatic as in the case of the lightest neutron capture elements, and this will always give us a very much nicer improve of both barium, lanthanum, and in particular cerium. We can judge the quality of our fit also with this term, which is again the distance of the best Pareto front model to the ideal point, so the origin in the chi-square parameter space. And you can see that for the heavier elements, it is almost half of the one that we get for the lightest elements, meaning that the solar scaling becomes less and less valid as we move towards lightest neutron capture elements. So if I have still time, I can show this very last slide in which we might ask ourselves if we then need different scaling relation. And if this different scaling relation can be found from other stars. So here, for example, I show you the observed abundance pattern of the two Honda stars in yellow and red. Everything is normalized to europium, so these stars that usually are under abundance with respect to solar and have an overabundance of the lightest elements with respect to the europium. Here you can see them as having the same europium abundance as the sun, with represented by the black diamonds, but of course they show the overabundance of the lightest elements. And then you have the Sneden and the Broder star in blue and in gray. They are more similar to the solar abundance pattern, but still show some differences when you go towards the lightest element. It's interesting that all the stars have a different strontium to yttrium ratio and zirconium to yttrium ratio than the one that is observed in the sun. You see that this ratio is actually bigger for all of the stars than respect to the one of the sun. That can explain the not so coherence that we actually had for the first S-process peak elements. So then we can play with the scaling relation. So instead of scaling with the solar R, now we can scale with one of the two Honda or the Sneden or the Roederer star. So we can also get rid of the iron in case we want to be more sure that our results are not influenced by other phenomena. And then we can plot the strontium over europium versus strontium, yttrium over europium versus yttrium, and so on and so forth. And you can see that here different lines correspond to different scaling relation. Of course, we will have a similar scaling, similar results when we scale to Sneden and to the Broder star, especially for strontium, zirconium, and barium, lanthanum, and cerium, for which the results are basically identical, but we will have a different results for the yttrium. On the other hand, we will have overabundance of the lightest elements, so strontium, yttrium, and zirconium, when we scale with the two Honda stars, and again similar results for barium and lanthanum when again when we scale with these two Honda stars. So probably the scenario is more complicated than just changing the scaling relation. So to conclude, I hope that I convinced you that galactic chemical evolution models are powerful tools to understand the formation and distribution of different chemical species in galaxies of different morphological type and different environments in general. Homogeneous models are useful for parameter space exploration and sensitivity analysis, and in particular they are needed when we are towards later times, so corresponding to higher metallicity, where we lose the stochastic imprint of individual events, which is averaged out by the subsequent stellar generation that we have. We can build, nevertheless, this self-consistent chain of models in which nucleosynthesis prescription are inserted in galactic chemical evolution model and compared to high-resolution observation, and any discrepancy can be used to repeat this cycle again. And then we can use chemical evolution model to answer important questions such as, are neutrons are merged, the dominant source of the arc process in the galaxy, and if not, is because of their frequency or of their delay or a combination of both. Do we need a second source? How can calibrate their nucleosynthesis? How can calibrate their delay and their rate? And is their process robust towards lighter mass? And as we see, if this is not the case, do we need a different scaling relation, or do we need a combination of different scaling relation? And with this, I conclude, and I thank you all for the attention.